As I said, we can change our shapes there. We can make us a little bit taller. We can turn our legs on an angle if you're constantly pulling on them. You see people who actually born, especially this is years and years ago, if you were walking like with your feet spread wide open, they used to put shoes backward on you to force your feet to go normal, straight. They put the left foot on the right foot on the left, and it turns your feet inside. And if you do this for a while, your actual bone will turn that way. Same thing, dentists do that. When you go to the dentist, if you have crooked teeth, they tie these braces to them and they hold them in place for a while, and that will force them to go in that direction. Well, you can do the same thing. Monkeys always hanging from trees. Their weight is pulling down their arm. So they have long, long arm. So if you're constantly pulling on something, eventually you're going to change the shape of it. If I constantly keep putting pressure on this, like on an angle like this, if I do it all the time, finally you leave the pencil, you come back, next day it's going to be buckled. That's what happened. This constant pressure on it all the time like this is going to put it in that position. You're going to change the look of it. You're going to deform that one. And changing the length of a solid, if you want to stretch it, keep pulling on it, you will make it longer. So the equation that will use that, it says the amount of force required to stretch something. So if you have a pipe and you want to stretch it, you have this pipe, let's say it's attached to the wall here so it doesn't move, and you want to stretch it, you start pulling on it. And it will change the length. If you're constantly pulling on it, this will get longer, not by a lot. So the equation F equals Y, which is Young constant, that's Y, times the change in L over the original length times the area. And Y, we call it Y because it's Young constant. And it changes from an object to an object. Again, steel is 20 times 10 to the 10. Copper, 11 times 10 to the 10. Glass is 6.2 times 10 to the 10. Bone, 1.6 times 10 to the 10. So, for example, if you go and you pick up, I don't know, 100 kilogram. Don't move. You're in the gym and you have 100 kilogram in your hand, walking with it all the time. You work in the gym. 100 kilograms is a lot of weight there. So you have to be like Popeye there. But you have 100 kilogram and you're carrying that walking around the gym 10 times a day. Each time for 5-10 minutes. You keep doing that. You look at the bone in your arm there. We'll take, which bone? The top one, the shoulder one. What is that bone called? Anyone?
Humerus, clavicle, scapula.
This one?
Humerus.
Humerus, okay. Let's give some dimension for it. Let's say the length of that bone, original length, is 0.3 meters, 30 centimeters. The area of the cross section looks round. If we can peel the skin, we'll see it looks round. And let's say the area is 5 times 10 to the negative 4 square meters. And if you dangle that 100 kilogram weight and you're constantly walking around with it, you will stretch your arm. By how much? Well, let's see. That's the equation I'm going to use. The force is the weight I'm holding. The weight is what? 100 times 9.8, which is what? Is that 980? Weight equals mass times gravity. Now, Young constant for bone is 1.6 times 10 to the 10. It's from the table. The change in the length over L0, the original length, which is what, 0.3, times what? 5 times 10 to the negative 4. Let's see what that number is. 1.6, 10 to the 10, divided by 0.3 times 5 e to the negative 4. .7 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. Delta L. What's delta L equal to? 980 divided by that number, which is 0.00037 meters. Huh?
So pretty much no change.
Minimal. How many centimeters? 0.037 centimeters. So 0.03 millimeters. It did change a little bit, but not a lot. That's the change in the length of your bone there. You can do bridges that way. Stretch on them, pull on them. You can even not just the length of it. You can change the shape sometimes. You can take a piece of wood, 2x4, and twist it. You know, put it in a machine, contraption, twist it, and let it sit for a while. When you take it out, it's going to be twisted a little bit there. It's not just the length of it. So if you want to do the area, the equation, instead of changing the length, we use y here. If it's an area, let's see what the equation might look like. So changing the shape. Of a solid there. I don't know if you ever took books and you stacked them there. You stack them straight up there, sitting like an If you take a lot of books, put them on the shelf, and sometimes some of these books will lean a little bit there. It will go crooked like this. And if you have a lot of them on it, I don't know if you can see the crooked there, instead of straight, they'll be a little bit crooked there. And if you have a lot of these books stacked on top of it, when you take the weight off them, that book stays like this. So we change the shape of it because of that constant force acting on that. So we can also change the shape of a solid shape like this one. Instead of looking like this, we can make it crooked, up this way, that way. And the equation for that is, again, you have a book like this. It used to be like this. But now you apply a force to it, and instead of being straight like this, it's crooked. It looks like this. Because you have a force pushing on it. That book is not normal. So that force, we call it F here, that was pulling on it, pushing on it. This is the area here. This is the change in X here. Used to be straight, now move that direction. L0 is this height here. So the equation says the force is equal to S, which is the shear now. Shear deformation, that's what S is. Times delta X, that's this gap, over L0, times the area. S is known as the shear deformation. And again, just like the other one, it's a constant, and here's a table for them. For steel, for bone, for copper, for brass, for aluminum, for lead, we have different value for S. Let's take this example because the book talks about pancakes. I like pancakes. At one point, my password was pancakes with a number in it. Can't remember what the number I used, like pancakes 11 or something. We have a stack of pancakes. They were like this, sitting on a plate. Now we apply a force to them. The pancakes look like this. I don't know if you can see them. So you can see actually they moved here. That distance is 2.5 centimeters. And the reason they moved, because we were pushing on that, there's a constant force. We were applying a constant force of 1.2 Newton. Now each pancake has a 13 centimeter diameter. The pancake is round. The diameter is 13 centimeters. And when you stack the pancake on top of each other, the height was 9 centimeters. Can you find what S is? What is the shear module for this one? Because notice when I look at the charge here, the shear deformation, I don't have one that says pancakes. What the number for it? Well, we can get what that number. We can find it by using the equation. Which equation? That one. F equals S times delta X over L0 times A. The force was 1.2. S, I'm looking for it. Delta X, that's this distance, 2.5 centimeters, which is 0.025 meters. By the way, I could have left this in centimeters, to be honest with you, because it's a ratio, right? 9 centimeter, 0.09 meters. What about the area? What is the shape of a pancake? Circle. Isn't that pi r squared? Times pi r squared. What's r? 6.5? 0.065 squared. Pi r squared. Looking at each pancake from the top is a circle. Radius is 6.5 centimeters, 0.065. So 1.2 equals S times what? 0.025. Oh, turn it on again. 0.025 divided by 0.09 times pi times 0.065 squared. Again, if I was good pushing all the buttons, 0037, can I get what S equal to? 1.2 divided by those numbers, 325.5. So the shear deformation S here is 325.5. We have one more, and that's changing the volume. Trying to think where you might see that changing of volume. Tires on a car. If you just park that car and walk away from it, like for a long, long time, when you come back, what happens to that tire? Probably flat bottom. The shape will change. So changing the volume of a solid. Okay. Again, why would the volume changes? Usually you have either increase or decrease in the pressure. Change the pressure, because there's a volume there. A balloon again. I'm taking that balloon in the plane. We go up in the air. What happens now? Less volume. I mean, the pressure is different, less. The volume increase. Come down, the pressure increases, the volume decrease. The equation for that change in pressure equals negative. Notice it's negative. It's backward, which means what? If this one increases, what happened to that one? Decrease. If this one decreases, that's what? Increase. Negative B times the change in V, the volume, over V0. B is a constant. It is called bulk modulus, and it changes from, again, object to object. I'll give you some numbers for B. These are some numbers: ice, oil, water, aluminum, copper, steel, gold. So it's a constant value there. So let's take an example here. I don't know what a gold double is. Anyone know what that is? Anyone knows? No? What a gold doubloon is?
A gold doubloon?
Doubloon, yeah.
It's a form of money, isn't it?
I don't know. Could be.
Let's Google it.
Is it?
Yeah.
Is it money?
Form of money. Yeah, it's what the pirates would have got there. It's a gold. Oh, yeah.
Oh, okay. Well, we learned something new today. What do you know? So it looks like this. Is it round shape?
Yeah.
Just like a coin, like a quarter? Okay. So here we go. We'll say it's a quarter. Looks like there's my picture in it. Pirate. There we go. There's a picture with one patch. It's not with a picture there. But it's a coin there. It's 6.1 centimeter in diameter. And 2 millimeters thick. The thickness, it's 2 millimeters. Remember, a centimeter is what? 10 millimeter, that's 0.2 centimeter. That's the thickness. It's dropped over the side of a pirate ship. Yep, there we go. What do you know? You were right, Mike. Pirates use that. When it comes to rest on the ocean floor, oh boy. So here's the water. It's going to fall in the water, and it sits right here. The floor is how deep it is. It's 770 meters deep, which means we calculate the pressure there. How much have the volume changed? What is the change in the volume? Well, a couple of things. Let's do a few things before we jump to that problem there. And do we know what's made out of? Gold. Yep, a gold, it says here. So we'll find what beta is. Since it says gold, beta for that, for gold, so we know what beta is. It's 22 times 10 to the 10th. It's made out of gold. So I know what B is. I'm looking for delta V. I need to find the change in the pressure. Well, it was in my hand on the edge of the ship there. So originally it was on it with atmosphere pressure. Now in the bottom, what do you have? You have atmosphere pressure plus the weight of the water pushing down. So the change, the difference between this and that is actually the depth of the water, which is what? Rho times gravity times height. Now, let's find out what that number. Rho is the rho of the water. Assuming it's salt water, rho is 1,030. Gravity is what? 9.8. And the height, which is what? 770. $10.30 times 9.8 times 770. It's 7.77 times 10 to the power of what? 1, 2, 3, 4, 5, 6. Well, 1, 2, 3, 4, 5, 6. 10 to the 6. Newton per Newton meter squared. That's the change in pressure. We need the volume. Well, this is what it looks like. It says cylinder looks something like this, the coin. I'm just exaggerating with the picture. It looks like this. So the volume is the area times the height. So it's the area times the thickness. Well, the area is pi r squared times the thickness. So pi, what's the radius? Diameter is 0.2. The radius is 0.1 centimeter. 0.1 divided by 100 to convert to meter, 0.001 squared. Oh, wait a minute. I'm sorry, that's the height, right? That's the height. Diameter is what? 6.1 centimeter. That means the radius is what? 3.05? 3.05 divided by 100 to convert it to meter, then square it, times the thickness, which is 0.002 meters. Square that number times pi times 0.002. 5.85 times 10 to the negative 6 cubic meters. So we know what the volume is. Last thing, let's calculate what change of V is. Change in pressure, 7.77 times 10 to the 6 equals negative, what's B equal to? 22 times 10 to the 10 times the change in volume over V0, which is 5.85 times 10 to the negative 6. And I should say the change in volume is going to be a negative, it's going to decrease. And I'm getting 2.06 times 10 to the negative 10. So it's not going to change by much. Cubic meters. So it really didn't change by much, by a small value. The volume shrunk just a little bit. You and I won't even notice it. But all that added pressure to it's going to reduce the volume, reduce it because it's negative. And that's deformation. The only thing left is change of phase. We'll do that on Monday, because I will need about an hour and a half for that.